analysis of DC to DC converter schemes using new type of efficient switching devices and magnetic materials for improved maximum power extraction systems from solar PV generation systems. Sir has also been the project director at the Ceramic Electrical Research and Development Center, an autonomous organization of Government of Rajasthan. Sir has also developed policy documents for CERDC Government of Rajasthan. Sir has guided many PhD and MTech students. Today, sir is here with us for a talk on design and implementation of improved power quality, voltage and frequency controller for small hydro-driven renewable energy systems. A very hearty welcome to you, sir. Over to you, sir.
Yeah. So, good afternoon. So, please.
Are you able to share your slides, sir?
Yeah.
Okay.
Actually, is my screen is visible?
Yes, sir. Your screen is visible, sir.
Okay. So today we will discuss about the voltage and frequency control of small hydro power generation systems. Okay. So I have worked in this area for many years. And first we will discuss about the analog controls, then we will discuss about the digital control implementation. So mainly we will discuss about the implementation aspects because of a lot of things. Being an expert in this area, electrical engineering area, people knows a lot of things about the small hydro power generation systems. So today we will discuss how to implement the control voltage and frequency controllers for small hydro power generations. And what should be the approach for developing a analog control, developing an analog controller, and what should be the approach to develop a digital controller for a small hydro power generation system. Okay. So first we will discuss about the analog control. Okay. So in a small hydro power generation system, we require an asynchronous generator. Okay. So generators may be classified broadly into two categories: asynchronous generator and asynchronous generators. So particularly for renewable power generation system, we always require asynchronous generators. Okay. So as far as asynchronous generators are concerned, there are mainly three types of asynchronous generators are available in the market, are in use actually. One is a self-excited induction generator, then DFIG, double fed induction generator, and third is the PMDC generator. Nowadays, people are also using PMSM generator. Okay, some other generators are also being projected in this area. But till now, in most of the installations, people are using these three generators. Okay, so but for very low power applications, so I am talking about very low power small hydro power generation like 1 kilowatt, even 500 watt, 2 kilowatt, or 5 kilowatt, or 10 kilowatt, or 20 kilowatt. Okay. So for that we require a single phase system. Okay. So today we will discuss how to develop a single phase small hydro power generation system for domestic and small industry applications in remote areas. Okay, where the water 24-hour falls from the mountains or some locations. Okay, so there such type of small hydro systems can be implemented. So here we will use single phase self-excited induction generator. Induction generator further can be classified in two categories: single phase induction generator and three phase induction generators. Okay. So for very low power applications, we may go for single phase induction generator. Okay. And if the power rating is very high or medium, so then we have to go for three phase induction generator. So today I am talking about the low power small hydro power generation system. So we will consider only the single phase self-excited induction generator. So a single phase self-excited induction generator is made of a single phase induction machine. This is made of a single phase induction machine. Single phase induction machine can be converted into single phase induction generator by electrically separating its both the winding. Okay, so single phase induction machine has two winding. Okay, so main winding and auxiliary winding. So when we use this machine as a motor, so both the windings are electrically connected. Okay, and a capacitor is connected in series with the auxiliary winding. Okay, so when we use the same machine for generator, we electrically separate both the windings, main winding and auxiliary winding, and we connect a capacitor across the auxiliary winding, and main winding is used to feed the power to the consumer load. So in this single phase induction generator, auxiliary winding is essentially act like an excitation winding. Okay, and main winding act like a power winding to feed the power to the consumer loads. Okay, so we have connected a capacitor across the auxiliary winding. Now the rotor, which is a spiral cage rotor in this single phase induction generator. So this single phase spiral cage rotor, sorry, this spiral cage rotor is mechanically coupled with the small hydro turbine. Okay, although we may also couple this rotor with the wind turbine or maybe diesel generator. Okay, so you may also replace the prime mover. Okay, but here the prime mover is a small hydro power generation, small hydro turbine. So a small hydro turbine is directly coupled with the rotor of the induction generator, but depending on the speed, actually minimum speed should be 1000 rpm. So if there is if the prime mover speed is less, then you may require some gears to increase the speed of that prime rotor. Okay, so this SCIG, single phase SCIG, can generate power from even I have experienced from 800 rpm to 1800 rpm. Okay, so in such a wide range it can generate the power. Okay, so we rotate this rotor using some external small hydro powered small hydro turbine, which is mechanically coupled with this spiral cage rotor. Now when we start rotating this rotor, some voltage is induced due to residual magnetism, some voltage is induced in auxiliary winding and main winding both. Okay, now because auxiliary winding is short circuited through the capacitor, so the current will flow through the capacitor. Okay, so when this very small voltage which is induced in the auxiliary winding, that will cause the flow of current in this capacitor. Okay, which is connected across the auxiliary winding. And because of the flow of current in this auxiliary winding capacitor, some reactive power will be injected into the system. Because of that reactive power, more magnetic field will be set up in the air gap of the induction generator. So this process will remain continue, okay, till the voltage will be built up to the its rated value. Okay. So again, because of now the flux in the air gap has been increased, so now more voltage will be induced in auxiliary winding, so more current will flow through the capacitor, so more reactive power will be injected into the system. Then again that reactive power will further increase the flux in the air gap of this induction generator. That increased flux will further increase the voltage across the auxiliary winding. Okay, so like that, due to this continuous process, this voltage will be continuously built up across the auxiliary winding as well as main winding. Okay, and this main winding voltage will reach to the 230 volt. Okay, after some time. So the value of the capacitor connected across the auxiliary winding will decide the no load voltage of the main winding. Okay, so we select the capacitor for our auxiliary winding in such a manner that a rated voltage is induced across the main winding at no load. Okay, and a very small value capacitor is connected across the main winding. That is not for the purpose of injecting the reactive power into the system. Okay, so here we have used a 1 microfarad capacitor across the main winding, that is used for to stop the voltage entering the voltage transient into the windings. Okay, so some voltage transient will come from the power electronic converter side, because of we are using power electronic converters for voltage frequency control. Okay, so this small capacitor will absorb all the transient voltage transients. Okay. Particularly the switching transients. Okay, in the voltage waveform. So sometimes this capacitor may be replaced with the RC filter. Okay. So usually this value of this capacitor varies from 1 microfarad to 5 microfarad, and the resistance means rheostat which is connected in series with this capacitor in real time may vary from 1 ohm to 20 ohm. Okay. So we adjust the rheostat in such a manner that all the transients are settled down. Okay. In the waveform, we observe on the DSO, we observe the waveform of the generator on the DSO, and we adjust the rheostat in such a manner that most of the switching transients are settled down. Okay. So now we have selected the value of auxiliary capacitor which is connected across the auxiliary winding in such a manner that a rated voltage of 230 volt or 220 volt, okay, depending on your requirement, may be developed across the main winding at no load. Okay. Now if you increase the further load, the system will require more reactive power. But now because the source of the reactive power is constant here, the value of capacitor which is connected across the auxiliary winding is a constant value capacitor. So that is not an adjustable value capacitor. So when we increase the load on the system, the voltage will be reduced. So this single phase induction generator has inherent poor voltage and frequency regulation. So when voltage will be reduced, the speed will also be reduced, therefore the system frequency will also reduce. Okay. So like that, when we load this system, because the voltage and frequency regulation of the generator is inherently poor, both will drop. Voltage and frequency both will be reduced. So now the issue which need to be addressed is to regulate the voltage and frequency under varying load condition. Under varying load conditions, we require to control the output voltage and frequency of the generator. Now there are three approaches which are in practice. First approach, in this first approach, what we are doing, we are connecting a dump load, adjustable dump load at the point of common coupling in parallel with the consumer load. In parallel with the consumer load, we are also connecting a dump load. Okay. And by varying the duty cycle of the IGBT switch of this dump load, we adjust the effective value of this dump load. Okay. And we adjust the effective value of dump load in such a manner that the sum of the consumer load and dump load remain almost constant. So whenever the consumer load will increase, dump load will decrease. Whenever the consumer load will decrease, dump load will increase. Okay. In such a manner, the total load across the generator will remain constant. When total load will remain constant, in that case, the require of the capacitance in the auxiliary winding will also be a constant value. So there is no issue. So we don't require a variable capacitance across the auxiliary winding because of the load on the generator has been made fixed. Okay. So you can say why we are using dump load. Okay, it will be less efficient system, but efficiency is not an issue here because of this is a small hydro system which is installed in the mountains where the water is falling 24 hours. Okay, even if you will not use the continuously, water will fall continuously. Okay. So in this system, if we use the dump load for system voltage and frequency control, there is no issue, there is no loss of energy because of energy is free of cost available here in this case. Am I audible clearly? Are you able to hear me?
Yes, sir. Yes, sir.
Okay. आप मेरी बात को समझ पा रहे हैं ना? अगर आप कुछ पूछना चाहें तो मुझे पूछ लीजिएगा बीच में, क्योंकि वो बड़ा इंपॉर्टेंट बात है, क्योंकि आप लोगों को इससे कुछ बेनिफिट होना चाहिए. ओके. आपको कोई बात हो तो बीच में पूछ सकते हैं.
Yes, sir. For the participants, the mic is disabled. If any participant wishes to ask anything, he should raise his hand and I'll allow the mic for him. Thank you.
प्लीज प्लीज। कभी कभी ऐसा होता है लेक्चर पूरा होता है तो क्वेश्चन ही भूल जाता है पार्टिसिपेंट।
जी सर।
लंबा लेक्चर होता है तो वो भूल जाता है, फिर लास्ट में
हाँ सर, पार्टिसिपेंट्स चैट बॉक्स पे भी टाइप कर सकते हैं सर क्वेश्चंस।
प्लीज प्लीज प्लीज, तो उसका कुछ आउटकम आना चाहिए ना लेक्चर का, इसलिए। ओके, तो आई मीन टू से दैट so in this first scheme what we can do, we can adjust the dump load, okay, value, effective value of the dump load across the consumer load in such a manner that total load is remains almost constant. Now there are three practices for changing this dump load. Okay, first approach, that was the voltage feedback based approach. Okay, so most of the researchers throughout the world have used the voltage feedback approach. In voltage feedback approach, what they did, they have taken system voltage as a feedback variable and they have compared that with the with a reference value, okay, 230 volt, and error is processed through some PI controller, and then the PWM is generated, and the IGBT switches, dump load IGBT switches controlled through those PWM signals, okay, generated by that PWM generator. So fundamentally here we are trying to maintain a constant voltage here. So that was the philosophy, that if the system voltage will become constant, then automatically the system frequency and power will also become almost constant. Okay. Now thereafter I started working in this area, so I proposed a new scheme. So as per that scheme, what I did, I simply changed the input variable. I have considered frequency as the input variable instead of voltage. Instead of voltage, I have considered system frequency as a feedback variable, because of in a induction machine system, the magnetization curve of the generator or induction machine either move in upward direction or in downward direction when we change the system voltage, sorry, system frequency. So whenever the system frequency will be varied, the magnetization curve of the induction machines will shift either towards upward direction or toward the downward direction. So now because of the magnetization curve itself has been shifted, and by this control we were earlier controlling the point of operation on that magnetization curve. Okay, so if we are controlling a point of operation in that magnetization curve and the curve itself has been shifted in the upward direction, then there is no point of controlling, because of automatically the system will lose the stability. So I have raised this issue before the international community, and then almost all people have started working in this area, and system frequency has been started taken as a feedback variable, and we got published this scheme in IEEE transactions on industry application. I also got one patent on this scheme. So because we have taken the system frequency as a feedback variable, it was very simple, actually concept was very simple, but somehow just by varying the feedback variable you may create a novelty. Okay, but for novelty we have to do the literature review. Okay, seriously, then you can find out the novelty in your system. Otherwise sometimes you have the novelties in your systems, new developed system, but you don't know what the novelty, and you are not able to prove your novelty. That is also an issue. Okay, so you should be you should have skill to develop your system, and you should do the proper literature survey to establish the novelty of your developed system. So here in this system we are taking system frequency as a feedback variable. So for that, in this control I have taken the system voltage as a sample, then using that zero crossing detector we converted that signal into a square wave signal. We have converted that system in, see here. See, this low frequency sinusoidal signal is the output of the generator. Okay. So using zero crossing detector, I have converted that into a square wave signal. Okay. So then I have fed that square wave signal. I'm in lecture. I'm in lecture. So this zero crossing detector converts this sine wave into a square wave. Okay. And I try to convert the frequency of that square wave into voltage using F2V converter. But practically in any generator, the frequency varies for 1 or 2 hertz only. Never this frequency varies from 50 hertz to 40 hertz or 50 hertz to 60 hertz. It may vary from 47 hertz to 53 hertz maximum. No further variation is possible in any generator in practical applications. So what I find, then when there was a variation of 1 hertz or 2 hertz, my controller was not able to make out that change in frequency. Because of this resolution of that V to F converter block was very poor. And I tried different type of voltage to frequency converter, frequency to voltage converter, but none of them was capable to converting faithfully the variation of one frequency into voltage. Then I developed a multiplier. Then I multiplied that error in frequency by 10. Then I find that when I multiplied that signal by 10, the starting point of that waveform was different. Okay. So because of the phase difference in different output waveforms, again the output of F to V converter was not okay. So then I had developed an analog PLL. Okay. So using that analog PLL, I had developed a frequency multiplier. Okay. So this frequency multiplier has logged the input and output frequency signals. Okay. So see, this ZCD output signal has been multiplied 10 times using that analog multiplier. So see, the leading and trailing edge of the ZCD output is logged with the trailing edges of the output of the F2V converter. Sorry, multiplier. Okay. So see, these edges are logged. Trailing and leading edges, both of trailing and leading edges of the ZCD output are logged with the output of frequency multiplier. So now this frequency multiplier is multiplying exactly. That is also very important practically. If you are multiplying a signal with 5 times scaling factor of 5 or 10 means 5 times or 10 times. So that multiplication, both the waveforms should be logged. Okay, input and output waveform in phase. Okay. So if they are not phase logged, that multiplication sometime it will be 10.1 time, 10.2 time, maybe 9.9 time, maybe 9.8 time, but it will not be exactly 10 times. So if you want to multiply any signal, okay, with some constant value, you have to have a PLL kind of system. Means phase loop must be there. Otherwise, the faithful multiplication is not possible. This is the main requirement in almost all digital and analog control systems. Okay. So even when you are using digital controls, you should take care whether the input and output are in phase lock or not. If the phases are not locked, then your multiplier will not work exactly, and the resolution of your control will become very poor, and your steady state error never will be the zero. Even if you are using PI controller, okay, your system will become so unstable that you will not be able to get perfectly stable system. Okay, so you irrespective whatever tuning skill you have for the PI controller, okay, you may even with the sliding mode control, definitely some steady state error with there, but with PI controller usually steady state error is always zero. Okay, but if the frequency multiplier, if you have a multiplier, frequency multiplier in your system, and if there is misalignment in this frequency multiplier, it will make your system so unstable that you will not be able to tune your system. Okay, and steady state error will be there all the time. Okay, and your research will not be acceptable by the international community. Okay, so now this is the novelty that I have introduced. These 2-3 novelties we have introduced in this scheme. So now we got the 10 time multiplied signal, output signal of this induction generator, and this 10 time multiplied output signal is fed to the F2V converter. So F2V converter converts the frequency into voltage, and output is the DC voltage. So the magnitude of this output DC voltage is proportional to the system frequency. Here you see, when we are varying the system frequency, how the output of F2V converter is increasing. Okay. Now this F2V converter output has been fed to, is compared with some error and being fed to the PWM generation, for PWM generation. Okay. So see, if there is some problem. Huh.
Yes, sir. Now it is visible. Yes, it is visible.
Okay. So now see in this diagram, see the frequency of the generator is continuously increasing cycle by cycle. हर साइकिल में देखिए टाइम जो है ना उसका कम होता जा रहा है साइकिल का टाइम. So the error signal is continuously increasing in each cycle. In this real time result, you may observe it very clearly. So how the frequency to voltage converter is capable of converting that variation in frequency into the voltage. And then this F2V converter output has been fed to the PWM generator. Okay, so that PWM circuit is generating the PWM output, and duty cycle is varying. Duty cycle of that PWM signal is varying from 0 to 1. Okay, so by increasing this, when the frequency increases, this duty cycle increases. When the frequency decreases, this duty cycle decreases. Okay, so when duty cycle will increase, the effective value of the dump load will increase. When duty cycle will decrease, the effective value of the duty dump load will decrease. So this variation in the effective value of the dump load will be adjusted, okay, according to the system frequency. So here in this scheme, we are maintaining a constant frequency so that the magnetization curve will not be shifted in any direction. Okay, so definitely it will significantly improve the stability of my system. Okay, that was the major claim. And when the system frequency has been made constant, frequency voltage automatically becomes constant. So maximum variation in the system voltage is possible. Variation is 1 volt or 2 volt only from no load to full load. Okay, so both were the voltage and frequency both was acceptable as per the IEEE 519 standards of the power quality. And the see here in this present scheme, we have removed the capacitor in the output of the 2-pulse diode rectifier. Earlier, people were using a big size capacitor in the output of this 2-pulse diode rectifier. So, a single phase rectifier is inherently linear load. It never creates any power quality issues for the system unless and until some inductive or capacitive load is not connected in the output of this rectifier. If any inductor or capacitor will be connected in the output of this rectifier, then it will increase the THD, and the THD may increase up to 40%, 60%, sometimes 90%, 99%. But if this single phase rectifier is feeding to a resistive load, it will not inject any kind of harmonic current into the system. But if you will connect a capacitor, but in almost all applications in single phase rectifier, we use a filter capacitor. So when we use a filter capacitor, that will inherently increase the TSD at the source side, and it will inject large amount of harmonic current into the system. So unless and until it is not required, don't use capacitor in the output of the single phase rectifier. And even if it is required, then try to have a capacitor of minimum possible value, जितने से काम चल जाए. ज्यादा वैल्यू कभी कैपेसिटर नहीं लगाना चाहिए. जितना ज्यादा वैल्यू कैपेसिटर लगाओ, पावर फैक्टर उतना ही पुअर हो जाएगा. And that will inject more amount of harmonic current into the system. So if you want to improve the power quality of your system, you should try to reduce the values of the capacitors which are connected in the output of the diode rectifier. So here what we did, we have removed a capacitor from the output of this single phase diode rectifier so that this dump load system becomes linear. So in previously reported system, people were using big size capacitor in the output of diode rectifier, and that was causing the total injection of total harmonic distortion approximately 30 to 40%. So, but in this system we have removed that capacitor. So see in this power quality performance that the generator TSD becomes 4.3%. Generator current TSD and generator voltage TSD is 4.1% now, which is less than 5%. Therefore, my system is meeting IEEE 519 standards of the power quality. So, by removing the big size capacitor in the output of this single phase rectifier, which is used in this dump load circuit, we have reduced the TSD at the source side. So definitely if you reduce the TSD, automatically the power factor will be improved. And if power factor will improve, means the system will require less and less reactive power. Maintenance cost of the system will decrease because of those harmonic current. Number of rotating magnetic field will be set up in the air gap of this generator, and that will cause large number of pulsations in this generator. So by removing or by reducing the size of the capacitor across the output in the output of single phase rectifier, you help the power system community. So you should try to reduce the value of capacitor which are connected in the output of the rectifiers, unless and until it is not required. So as being a designer. So see, this is the photograph of the dual controller. Okay, so these are the power supply sections. Various power supply required to operate these different sections. So this is ZCD section, this is frequency multiplier and PLL section. This is F2V converter. This is buffer inverter. Then this is the PWM generator slice. Okay, so it is like that. So this is all about this analog controller. Okay, so that's how much time now I have. आपको मैं डिजिटल कंट्रोल भी कंप्लीट कर पाऊंगा. आप कितना टाइम और देंगे मुझे?
सर जितना आपको लगना हो.
अच्छा ठीक है. तो
means sir, how much time you require, sir? You can take, sir.
45 minutes is. Will you give me?
Yes, sir. You can take, sir, 45 minutes, sir.
Okay. So see, this result shows the system performance under varying prime mover speeds. With this controller and without controller. So see the left side figure shows this is the real time recording that we have recorded on a power analyzer, Flip 43B power analyzer. So see, here we have vary the load, okay, in steps, okay, and see the variation in the system frequency. So variation in the system frequency is of approximately 2 Hz from no load to full load. But using this controller, see the right side figure, the variation in the frequency only 50.1 Hz to 50.2 Hz, only 0.1 Hz variation is there. Without controller, 2 Hz variation was there. So error has been reduced 20 times. And this variation in point of 0.1 Hz, variation in frequency of 0.1 Hz is acceptable by the international community, by the different agencies, because of this is a renewable system. So in renewable systems, the standards are different. But as far as intracontinental grids are concerned, variation in the frequency of variation of 0.1 Hz in the frequency is not acceptable. But in renewable power generation systems, the variation of up to 0.5 Hz is acceptable. So here the variation is only 0.1 Hz. Okay. So it is acceptable as per the IEEE standards and other international standards in this area. And see here in this slide, this is also recording in real time on Fluke 43B power analyzer. So left side figure shows the variation in the consumer load and right side figure shows the corresponding variation in the dump load. So see, when we started decreasing the consumer loads in step, dump load automatically increases in step, in equal step. And when consumer load increases, the dump load decreases. Here we have taken the system frequency as a feedback variable. So this variation will be corresponding to the maintaining the system frequency. And if the system frequency is maintained constant, system voltage will be maintained automatically. And system voltage is maintained constant means the reactive power requirement of system will become constant. Okay. And this is the response of the system under varying input mechanical power delivered to the prime mover of the induction generator. In seasonal variations, usually the output power of the small hydro turbines is considered to be constant. In all renewable energy sources, in all type of renewable energy sources, till date I have studied. I have also worked on the wind power generation system in real time. I worked in solar PV power generation system. Okay. In some other systems also I tried to work. But I found that small hydro is the most reliable renewable energy source. The limitation with this source is the site specific. Usually such sources are available in remote locations, in hilly areas. But in Madhya Pradesh, there it may be some location I don't know about the geography of very much about the geography of the Madhya Pradesh. But when I travel through the Madhya Pradesh, I saw a lot of mountains are there in the Madhya Pradesh. So I think there may be possible sites for installing the small hydro power generation systems in the Madhya Pradesh also. But there are a lot of sites in Uttarakhand for such systems. But this is highly reliable system. Almost stable system in comparison to other renewable energy systems. Because of in wind, the input power variation, the input power of the prime mover are very high. Usually that fluctuates. Anytime it may be changed. In solar it is also like that. But as far as small hydro is concerned, the input power delivered by the small hydro turbine to the generator is almost constant. But it varies in seasonal changes. सो जब भी सीजन्स में चेंज होगा, सर्दी से गर्मी आता है, गर्मी से सर्दी आता है, तो पहाड़ों से गिरने वाले पानी में बदलाव आने लगता है, उसके रेट में चेंजेस आता है. So my controller is also addressing that issue. Being a designer, this is my responsibility to address all the issues. So we have also addressed the dynamic issues. When the prime mover input mechanical power delivered to the prime mover will vary, see the system frequency is constant. Only the variation in the system frequency is 0.1 Hz. Okay, so that shows that my system is also stable when under varying input mechanical power delivered by the small hydro turbine to the generator. So another beauty of this scheme is this is governor free generator. This generator does not require any speed governor for frequency control. Frequency is being controlled without any speed governor. My controller is also functioning like a speed governor. It is maintaining system voltage, system frequency, and also maintaining a constant speed of the generator. So usually speed governors are used for the system frequency control. That is not required here. So that will significantly reduce the cost of the system. So see, the total cost of this controller is not more than 200 rupees for a small system of 1 kilowatt. And the cost of the small single phase induction generator is only 1000 or 2000 rupees. So in 2500 rupees or 3000 rupees, maximum may not be more than 5000 rupees. So within 5000 rupees, you can install a 1 kilowatt or 500 watt power generation system in any mountain in hilly areas where the water is falling. आप 1 इंच का 2 इंच का एक पाइप लगा दीजिए, 1 इंच डाया का 2 इंच डाया का एक पाइप लगा दीजिए, and your pump, you may convert pump into turbine, so pump will act like a turbine, so that is called PAT system, pump as turbine system. So the pump will act like a turbine. Okay, so आप एक केवल कुछ पाइप लगा दीजिए, पंप पैड सिस्टम से उसको कपल कर दीजिए, कनेक्ट कर दीजिए, and it will generate 1 kilowatt power continuously day and night without any cost. That is the beauty of the system. And the life of induction generator is comparatively very high, and maintenance cost is very less in comparison to any other machine known till days, means reported in the literature. So induction generator induction machines has lowest maintenance cost among all the other machines, electrical machines reported in this area. So maintenance cost of the induction generator will be very less. Another advantage of this scheme is the induction generator has inherent short circuit protection. Means if you will short the output wire of the generator, it will not burn away. It will not be damaged. Whenever you will short the output voltage will become 0. So it has inherent short circuit protection. If you have a 26 ampere generator, so it may not generate more than 26 ampere under any condition. So even if you will short circuit it, initially 26 ampere will flow, then this ampere will become 0 and generator will become demagnetized. So it has inherent short circuit protection. Now we'll discuss the digital control scheme for this. In this digital control scheme, induction generator is same, a small hydro turbine is same, a capacitor is connected across the auxiliary winding, and the value of this capacitor connected across the auxiliary winding is determined in such a manner that a rated voltage will be induced across the main winding. Now, the problem will come to the picture when we will increase the load. When we increase the load, the system will require an adjustable reactive power. In dump load system, what we did? We have made that load constant. In this advanced scheme, we are also injecting an adjustable reactive power through the voltage source converter. And that is also compensating all the harmonic current demanded by the load, nonlinear loads. So that this system is capable of feeding power to the nonlinear load also. The previous scheme that we have reported, that is modified electronic load controller system, that MELC based system. That modified electronic load controller based scheme was capable of feeding power to the linear loads only. But nowadays, most of the loads are non-linear in nature. Mobile charger, laptop charger, UPS charger, inverter charging system, VFD drives. Almost all these systems are non-linear. Even LED lights. These systems are non-linear. Non-linear means they demand non-sinusoidal current from the source. When a load becomes non-linear, when the shape of the current of that load is not same as the shape of the source voltage. If the voltage shape is square wave and current shape is also square wave, means load is linear. If voltage shape is sine wave, sinusoidal, load current wave shape is also sinusoidal, means load is linear. If voltage waveform is triangular voltage waveform, load current waveform is also triangular, means load is a linear load. But if the shape of the voltage waveform is sinusoidal and the shape of the current waveform of the load is a square wave or of some other shape, maybe triangular, maybe square wave, maybe spiky, then system is non-linear. So for a sinusoidal voltage source, non-sinusoidality may be defined as a non-linearity, may be considered as a non-linearity. And total harmonic distortion is a measure of non-linearity in the waveform. Sorry, non-sinusoidality in the waveform, sorry. But non-sinusoidal current never confirm that the load is non-linear. Load will be non-linear when the shape of the load current and load voltage will be different. whenever there will be the difference in the shape of the load current and load voltage in any system, it confirms that load is nonlinear. And all the nonlinear loads inject a large amount of harmonics into the system. So once the harmonics current are injected into the system, only the voltage source converter based controller can mitigate, can compensate those harmonic currents. So then you have to have voltage source converter. अभी तक जितनी रिपोर्टेड टेक्नोलॉजी है, रिपोर्टेड लिटरेचर है, उसमें कहीं पर भी आपको हार्मोनिक करंट को कंपनसेट करने के लिए एक बार इंजेक्ट कर दिया है तो कंपनसेट करने के लिए आपको VSC चाहिए, वोल्टेज सोर्स कन्वर्टर. So here we are using single phase voltage source converter. This voltage source converter is consist of 4 IGBT switches, 1 DC link capacitor, and DC link capacitor at DC side, and an interfacing inductor at the AC side. And this voltage source converter is performing number of functions simultaneously. It is controlling the system frequency. No, sorry. In this scheme, this is controlling the system voltage. This is controlling the system voltage by supplying an adjustable reactive power to the system. The voltage source converter is capable of supplying an adjustable reactive power to the system. Means this VSC will act like a 10 kVAR capacitor. In the very next sampling time, it may act like a 15 kVAR capacitor. Then it will become 20 kVAR capacitor, and then it will become 100 kVAR capacitor. Then it will become 2 kVAR capacitor. Within a 40 microsecond, that is equal to the sampling time. In every sampling time, it can change its reactive power value. So by how much reactive power is required to be injected into the system, that will be calculated by the control algorithm. And based on that decision, the DSP controller will generate the gating signal for this voltage source converter. And the voltage source converter will adjust the reactive power being pumped into the system in such a manner that system voltage become constant. So therefore, for controlling the reactive power compensation in the system, we take system voltage as a feedback variable. In all electrical systems, रिएक्टिव पावर वोल्टेज की मौसी है. इन दोनों का पूरा गठबंधन है. You are controlling reactive voltage means you are controlling reactive power. Both are almost same. So this voltage source converter can supply an adjustable reactive power to the system in such a manner that system voltage is maintained constant. Now, the quality of this reactive power compensation will be evaluated in dynamic operating conditions. Well, if there will be a sudden change in the load, suppose load is increased from 10% to 100%, so there will be sudden change in the reactive power demanded by the system. So now the rate of increase of the reactive power compensated by this voltage source converter will become important. Therefore, your voltage source converter should be capable of compensating the reactive power into the system at a very faster rate. In order to meet the control requirement in order to meet the system stability requirement under dynamic operating conditions like sudden load change, load perturbation condition. So under varying load, under sudden change in load, our voltage source converter must be capable of compensating the reactive power at the same rate. Therefore, we develop a neural network and we made the learning rate adjustable. And by varying the learning rate, we have made the system fit for dynamic operating conditions. But in artificial intelligence based system, neural network based system, the learning rate is very high. That is not always good. The learning rate of your system is high. That is very good in dynamic operating conditions. But that high learning rate will make your system unstable under steady state operating conditions. तालिबान बहुत बढ़िया है, अगर लड़ाई चलती रहे तो बंदूक लेके बैठा ही रहेगा, पर जब शांति हो जाएगी तो समस्या हो जाएगी, क्योंकि उसको तो बंदूक ही चलाने की आदत है. तो लर्निंग रेट बढ़ा देना बहुत अच्छी बात है, क्योंकि कोई भी डायनेमिक सिचुएशन आई तो तुरंत मिटिगेट कर देगा. पर प्रॉब्लम ये हो जाएगी जब कोई डायनेमिक सिचुएशन नहीं होगी, जब सिस्टम स्टडी स्टेट में आ जाएगा, जब कोई लोड में फ्लक्चुएशन नहीं है, कोई प्राइम और स्पीड फ्लक्चुएशन नहीं है, सिस्टम में कोई फ्लक्चुएशन नहीं है, कोई डायनेमिक सिचुएशन नहीं है, तब वो सिस्टम की क्वालिटी को खराब करेगा. और कहीं सिस्टम में यूजुअल वेरिएशंस को भी पैरामीटर वेरिएशंस मानेगा वो, और आपके सिस्टम को बार बार अनस्टेबल कर देगा. मतलब ऐसा कि कोई बच्चा भी चिल्लाए तो बंदूक लेके पहुंच जाएगा वो. So it is like that. So the learning rate of your neural network based system should be adjustable. So we have made that rate of learning adjustable in such a manner that it becomes high at dynamic situation, become very low under steady state situation, so that the sinusoidality of the current will be improved under steady state operating conditions. Another objective of using this voltage source converter is the harmonic current compensation. My control algorithm continuously detect the magnitudes of individual harmonics, cycle by cycle. How much magnitude of third harmonic is required? How much magnitude of fifth harmonic is required? How much magnitude of seventh harmonic is required? The equal amount of harmonic currents are generated by this voltage source converter and directly fed to the load. Therefore, that nonlinear load will not demand any harmonic current from the source. Now, this harmonic current compensation through this voltage source converter again can be achieved using two control techniques. One is indirect control technique, another one is a direct control technique. 99.999% cases, people use indirect control scheme to compensate the reactive power, harmonics. Compensate the harmonics. In almost all cases, people use indirect control scheme because that is simple, less complex. And in almost all cases, it has better performance. I implemented both these schemes in real time for different type of scheme, different type of topologies. I found that we don't require direct control technique. Indirect control technique is sufficient. But if the source current is not sinusoidal, sorry, source voltage, if the source voltage is not sinusoidal, then you have to have direct control technique. But fortunately, all the electrical generators are sinusoidal generators. But if your system voltage will have the shape of waveform other than the sinusoidal, then this indirect control technique will fail. जितनी दुनिया में आप डी स्टेट काउंट की जितनी कंट्रोल टेक्निक देख रहे हो, ये सब इनडायरेक्ट कंट्रोल है. बहुत ही रेयरली कुछ लोगों ने डायरेक्ट कंट्रोल पे कुछ पेपर लिखे हैं, रिपोर्ट किया है. इनडायरेक्ट इसीलिए सभी जगह चल जाता है क्योंकि सभी जनरेटर साइनसोइडल. अगर शेप वोल्टेज का चेंज हो जाए, then this indirect control will not work. Otherwise, the indirect control is really excellent. Very simple. And it has less calculation burden. If the calculation burden of the control algorithm will be reduced, the cost of the controller will be reduced. So, in this indirect control technique, what we do, we develop a reference sinusoidal current signal. And that is the fundamental component of the load current. So using the different control algorithm, we detect the fundamental component of the load current. And we force the generator to supply only the fundamental component of the load current. And we do the switching of the switches in such a manner that generator is bound to supply only the fundamental component of the load current. And fundamental component is always a sinusoidal signal. And now because the generator is only supplying the fundamental component, all the harmonic current component will be supplied by the voltage source converter. ये ऐसा ही है कि आपने आपके दोस्त को कहा कि बस तुमको तो गाड़ी में पेट्रोल ही डलवाना है, बाकी तो अपन घूमने चल रहे हैं. तो बात ठीक है कि अब आगे चाय वाय का सब पैसा आप ही को देना पड़ेगा क्योंकि वो तो खाली पेट्रोल ही डालेगा गाड़ी. But in direct control techniques, algorithm is required to detect the magnitude of individual harmonics. इनडायरेक्ट कंट्रोल में तो हमने ये नहीं पता लगाया था कि थर्ड हार्मोनिक्स का मैग्नीट्यूड कितना चाहिए लोड को, फिफ्थ हार्मोनिक्स का मैग्नीट्यूड कितना चाहिए, सेवंथ हार्मोनिक का मैग्नीट्यूड कितना चाहिए. That we have not calculated in the control. Just we have put the restriction on the generator that it will supply only the fundamental component of the load current. Nothing else we have done. But in direct control, we have to calculate the requirement of the magnitude of the required magnitude of each individual harmonic current. How much magnitude of third harmonic is required, how much magnitude fifth harmonic is required, how much magnitude ninth harmonic. So definitely that will increase the calculation burden on the system. But if the waveform of the generator is distorted, and we have implemented an indirect control. Your power factor may not be unity at any case. So that is why it is very much important that there should not be any harmonics in the voltage waveform of the generator, the system, for proper functioning of indirect control based scheme. Now the next objective of this voltage source converter is to maintain the power factor. So this VSC can maintain a unity power factor from no load to full load under varying load conditions, under varying nature of the load, with RL load, with RC load, with battery charger load, at any load, this VSC can maintain unity power factor. Power factor is reduced because of two reasons in any system. One, due to the reactive power demanded by the load, or due to the harmonics. If load is demanding harmonics, power factor, system power factor will be reduced, the source side power factor. And if the power factor is reduced because of the harmonics, you have to have such type of active filter in your system. VSC based active filter. That can make your power factor unity. And this converter can also be used for the system frequency control, for active power balance. But those two objectives are not the part of this scheme, this current scheme, whatever is shown here. Because of, for the system frequency control and power balance, we are using here the dump load circuit. That is another loop. So here, this dump load is working, and the control scheme for this dump load is similar as we have discussed in for previous case. The value of this dump load is adjusted, and system frequency has taken as a feedback variable, and that system frequency compared with the reference system frequency, and error is processed to PI controller, and then the output of PI controller is fed to the PWM generator, and output of PWM generator is fed to this IGBT. But here we have connected a big size capacitor. And the output of rectifier. That is not advisable. But if you remove this capacitor, you have to have all the 4 diodes of high frequency. Although this is not desirable to have this big size capacitor in the output of this filter capacitor, a rectifier, but मेरे को ये लगाना पड़ा क्योंकि उस समय मेरे पास हाई फ्रीक्वेंसी डायोड थे नहीं. High frequency diodes are very costly. So that time in laboratory, the high frequency diodes were not available. So I used the power frequency diodes. So, but that power frequency diode will not work on high frequency, though. Therefore, in that case, I had to have a DC filter capacitor. That is why I connected here. But now I have VSC, which can mitigate all the harmonic current injected by this single phase rectifier filter load. So all the harmonics injected by this dump load has also been mitigated by this voltage source converter. So it is still not creating any problem. But honestly speaking, it will increase the burden on this voltage source converter. So that will increase the rating of the voltage source converter. That is another thing. But I will be having a limitation in my laboratory. That time. This scheme I implemented many years back. So this dump load circuit is controlling the system frequency and maintaining a power balance in the system. And system frequency is working as a feedback variable. In this DSP controller, there are four input variables: source voltage, source current, load current, and DC bus capacitor voltage, DC bus voltage. This controller required the information about all these four variables in each sampling time. And based on the information made available by the sensors to the controller about these four input variables in every sampling time, controller execute the control algorithm and gives the decision in the output. Suppose the sampling time of your system is 40 microseconds. So your controller is required to execute that loop within that 40 microseconds, say maybe 36 microseconds, maybe 35 or 30 microseconds. But the sampling time should be more than the time required by the controller to execute the complete loop. Otherwise, your control will become failed. So overall, this system is controlling system frequency, system voltage, it is maintaining power balance, it is mitigating all harmonic current, it is compensating the reactive power. Okay, it is also controlling the system power factor. So number of objectives are achieved in the system. So see, this is the design. See, in an induction generator, usually its efficiency is maximum at one point of operation. So that is the leaky minimal disturbance theory based control algorithm that I had developed to implement this scheme. And this scheme is published in IEEE Transactions on Industrial Electronics. And it was the first scheme of single phase self-excited induction generator which was published in IEEE Transactions on Industrial Electronics. They accepted this scheme not because of what I have explained to you till now. IEEE Transactions on Industrial Electronics accepted this scheme for publication because of using this scheme. I operated the induction generator at a single point of operation, where it was giving the maximum output power. And that I have made possible by supplying the reactive power at very faster rate under dynamic operating conditions. So system was operating at maximum efficiency operation, point of maximum efficiency operation under all steady state and dynamic operating conditions. So because of that, my 3.7 kilowatt generator generated 5.5 kilowatt output power. The generator was designed to generate 3.7 kilowatt. By using this single point control technique that I had developed, the same generator has generated 5.5 kilowatt output power. That was the novelty of this scheme. I got a patent on this scheme. I also published paper in IEEE Transition Industrial Economics. The same scheme. So this LMDT is also, both of these schemes are available on IEEE Explore. You may also read those papers. So if you have any problem, I can also send you the same. This is the control algorithm, and these are the hardware results, experimental results. See, 5.5 kilowatt power has been generated at 24 ampere current. See the second result. Generator was designed. The generator was designed to generate 3.7 kilowatt output power at 26 ampere. Here the same generator is generating 5.5 kilowatt power at 24 ampere without increasing the stator current. We have increased 33% more power. So in any induction generator, if you operate your generator at single point of operation corresponding to the maximum efficiency, you can get 33% more power. So that is also neural network based control scheme. I also received 1 lakh rupees cash prize from Ministry of Power and Power Grid in a competition at Pragati Maidan in Grid Tech 2015 for the same scheme. All these single phase machines are 33% derated in comparison to their 3-phase counterparts. Like, consider 132 frame size of induction machine. In a 132 frame size, you can wind 7.5 horsepower machine for 3-phase configuration. For 3-phase configuration, you can wind 7.5 HP in 132 frame size. But for the same frame size, if you wind a single phase induction motor, then you have to wind 5 HP only. Same frame size में 3 phase तो wind हो रहा है 7.5 HP. उसी फ्रेम के अंदर अगर सिंगल फेज वाइंड करेंगे तो होगा 5 HP. 33% डीरेटेड हो जाता है. इसीलिए बड़ी साइज की कभी सिंगल फेज मोटर नहीं आती इंडक्शन मोटर, क्योंकि सिंगल फेज मोटर का साइज हमेशा 33% ज्यादा होता है सेम कैपेसिटी की 3 फेज मोटर से इंडक्शन मोटर. बट यूजिंग दिस कंट्रोल आई इंक्रीज द जनरेटेड पावर बाय 33%. So now we are able to wind 5.5 kilowatt machine in 132 frame size. अगर 3 फेज वाइंड करते तो भी 5.5 किलोवाट कर पाते. अब हमारे कंट्रोल के साथ में सिंगल फेज में भी आप 5.5 किलोवाट वाइंड कर पा रहे हैं. So that was the another novelty of this scheme. So see result D. Load current is almost square wave. See figure E, the total harmonic distortion of the load current is 39.3%. See figure G, the total harmonic distortion of the dump load current is 75%. Even then see the figure C. In figure C, the THD of the generator current is only 4.3%. So it is meeting IEEE 519 standards of the power quality. THD is still less than 5%. Consumer load has 39-40% THD. Dump load has 75% THD. And my VSC has compensated all those harmonic current. And see, there is no harmonic current in this SEIG current, generator current, figure C. So all the harmonic current has been mitigated. And this is the performance with the linear load. Definitely when system is capable of feeding non-linear load, it will also be capable of feeding the linear load. And this is the dynamic system performance when we suddenly increase or decrease the load current. My system is maintained constant, voltage and frequency of the system are maintained constant. And that proves the validity of my system. So now the floor is open for query. So you can ask any query if you have. I think I should not check your patience.
Hello, dear participants. Please unmute yourself and you can ask any questions. It is a big opportunity for all of you to interact with Ujjwal sir.
You can ask any question related to any other renewable energy source. If you have any problem in power electronics laboratory, in your hardware implementation, in your research, any problem if you have in your laboratory, you can ask. Even if you have problem in basic electrical engineering laboratory or any hardware.
That's great, sir. We are really thankful to you that you are opening this forum to ask any queries related to electrical engineering.
There was one participant who has been asking a question in every session regarding some hardware problem. I remember him. If he wished to ask, because sir is having a very good hand in hardware. एक कोई participants था जो पूछते थे हर कुछ माइक्रो और विंड टर्बाइंस को कंबाइन करने वाला. I am not remember his name. Is he present right now? I think he's not online, maybe.
Yes, sir. Yesterday might be, sir. Reddy sir was there, sir. He was asking for them.
He was asking for some problem. Mr. Reddy, are you here right now? There are no questions and no queries.
Oh, okay. So,
shall we formally end this session, sir?
Yeah.
When I saw the slides of sir with D-Space 1104, I got the remembrance of my PhD thesis also when I was working for a direct torque control drive and all this hardware and all. So all the faculty members and research scholars who have been working in the area of power electronics, drive, renewable energy, if they will develop a hand in hardware, it will definitely give them a good publication. That's what I feel, and that's what sir has explained to these during his slides. Sir, it was a very wonderful lecture, and we feel that I am planning to organize one more FDP, which will be totally based on case studies of power electronics and drives application for research scholars. And we look forward for your lecture in that FDP also, sir. So on behalf of Electrical Engineering Department and the organizing committee of this faculty development program, I extend my heartiest thanks and gratitude to you, sir, for delivering this lecture to us. Thanks again, sir.
Thank you. Thank you, sir. Thank you, sir. Thank you, madam. Thank you, sir.
Ritu, you can make some announcement regarding our valedictory and test, or our Narayan sir will give that. Who is going? Narayan, you are going to?
Okay, sir. So, dear participants, after a short break, sir, should we start at which time? 2:15? Sorry, sir, you are not audible. Hello.
Right now
sir,
it is 2 p.m. Yes.
Yes.
Right now it is 2 p.m. Can we start at 2:10 or 2:15?
So participant, this is for you. So you people have to tell us. Are you guys are comfortable at 2:15?
Yes, sir.
15 or 250?
Yes, sir. No issue.
215, 15, I think.
1515.
215, no, sir.
It is comfortable.
Yes, sir.
Thank God I have heard.
Thank
that-
you. So after a short break of 10 minutes. So after a short break of 10 minutes, we are meeting again.
So 215 is
And
comfortable.
then we will have a short discussion. And then we will float exam. So please be ready for the exam. There are very simple questions, so don't worry. You have enough time to attempt the questions. Thank you.
Thank you.
Short break of 10 minutes. We are meeting again.
Sure,
Thank you
sure.
very much.
And on behalf of the electrical department, I want to thank our HOD sir, who is also the convener of this FDP program, and Bhupen Singh sir, Professor Bhupen Singh sir, who is the coordinator of this program for organizing such a wonderful FDP program and inviting eminent speakers who had enlightened all of us. Along with that, I would also like to thank Mr. Pankaj Sarasya sir and Mr. Narayan Gupta sir for helping in coordination and for the easy conduction of this FDP program. Without your help, this would not have been possible. Thank you so much, all of you. And thank you all the participants for staying with us and making this FDP a success. Thank you so much.